Hello. In the last lecture, we have studied about second fundamental form and normal curvature of a regular curve inside a surface. In this lecture, so we will give some examples corresponding to second fundamental form. Let us begin. Let us take a unit sphere first. So let S2 be the unit sphere. So what is S2? So S2 is the collection of all XYZ belonging to R3 such that x square plus y square plus z square is equal to 1. So we know that this S2, it is a regular surface in R3. And now let us take a point in S2. Let me draw this unit sphere. So these are my coordinate axes. And this is my unit sphere. And this P is this point on this unit sphere. Okay. And now let us take a tangent vector V. So V is a tangent vector to the sphere at the point P. So V belongs to TP S2. So suppose this is my tangent vector V. And now let us take this curve. So let alpha t equal to P cos t plus V sin t. Okay, so let us also assume that this tangent vector I have taken it to be unit vector. Okay, so now alpha is a curve on this unit sphere. So why this alpha? It is a curve in the unit sphere. So if I take the norm of alpha and take the square of that thing, so norm alpha t squared, so this will be equal to the dot product of alpha t with alpha t. So which is equal to P cos t plus V sin t dot product with P cos t plus V sin t. So this is equal to P dot P cos square t plus twice P dot B cos t sin t plus V dot B sin square t. So now this P, it belongs to the unit sphere. So therefore, norm of P is equal to 1. So this will imply that norm of P square is also equal to 1. So norm of P square is P dot P. So this implies that P dot P is equal to 1. Okay. So now P dot B is equal to 0 because P, the vector P, here it is orthogonal to the tangent vector B. So P dot B is equal to 0. B is orthogonal to the tangent vector B is orthogonal to the vector T. And B I have taken to be unit vector, so therefore B dot B is also equal to 1. Okay, so therefore from this above equation, norm of alpha t square, so this is equal to cos square t plus sine square t, which is equal to 1. And this is true for all t. So this implies that norm of alpha t is equal to 1. So this implies that alpha t, it belongs to the unit sphere. Okay. So I have a curve inside this S2 such that the tangent vector at point P of that curve is the vector B. And this curve, in fact, so it is the red circle passing through the point P. Okay. Yeah. So why this curve it passed through point P? So if I take alpha 0, so this is equal to P. And now let us compute alpha dot 0. So alpha dot 0, it will be equal to what? So take the derivative of this alpha at the point t equals to 0. The derivative of this alpha t, it is minus p sine t plus b cos t. And this is evaluated at the point t equals to 0, so which is equal to p. Okay, so we have a curve alpha passing through p whose velocity vector at the point 0 is equal to p. Okay, so this curve alpha, it is a unit speed curve. Okay, so why it is unit speed curve? So if I take alpha dot t and take the norm square, which is again equal to alpha dot t dot alpha dot t. Okay, so again by the same type of computation, so you can show that this is equal to 1. So this will imply that norm of alpha dot t is equal to 1. So alpha is a unit speed curve. And what is the definition of this curvature of this alpha? So curvature of alpha at alpha t is kt equal to norm of alpha double dot t. And what is my alpha double dot t? So this is equal to minus p cos t minus p sin t. And norm of this alpha double dot t is equal to 1. So this will imply that the curvature, so this is equal to norm of alpha double dot t, which is equal to 1. Okay. Okay. So now observe that. So this alpha double dot t is normal to the surface. Okay. Note that this alpha double dot t is equal to minus of this alpha t. So alpha t, it is a point on this curve. So alpha t is this vector, and alpha double dot t is just the minus of alpha t. So it is opposite of the direction of the vector alpha t. Okay, so now let us take this unit normal vector field on S2. Let NP be inward normal vector field, inward unit normal vector field on S2. So then this n of alpha t, it will be equal to alpha double dot t. Okay. So therefore, the angle between the normal capital NP, so this capital N, it is the normal to the surface. And the normal small np, so it is small np, it is the normal to the curve alpha. Is equal to 0. Okay. So here, what is the normal to the curve? It is just alpha double dot t. So n, small n alpha t is just equal to alpha double dot t. Okay. So therefore, the normal curvature at alpha t is equal to KNP cos of 0. So where this KNP is equal to 1. So already we have seen that this KT is equal to norm of alpha double dot T, so which is equal to your 1. Okay. So therefore, so this will be equal to 1 multiplied by 1, which is equal to 1. Therefore, the normal curvature at alpha T is equal to 1. And what will be my differential of this unit normal vector field NP or the Gauss map N? So dNP of B, so this will be equal to minus B. Okay, so what will be the second fundamental form? So pi PB, so it is the second fundamental form. This will be equal to inner product of minus of inner product of dNP B with B. So which is equal to norm of B square. Now instead of inward unit normal vector field, if you have taken outward normal vector field, then what we will get is the following. So if n was the outward unit normal vector field, then the second fundamental form will be equal to minus dNP minus inner product of dNP B with B. So which is equal to minus of norm B square. Okay, because here if you compute dNP B, so this will be equal to B. Okay. So now let us take another example. Let us take a cylinder in R3. And let us take a point P in C and B be a unit tangent vector in C. Okay. Also observe that if I take this map N from this cylinder to R3, so N of x, y, comma, z is equal to x, comma, y, comma, 0. So N is a vector field on R3. So N is a unit normal vector field on R3. normal vector field not on R3, it is on C. So N is a unit normal vector field on C. Okay. Now let us take this vector B, which is in the tangent plane. Let us first take it to be parallel to Z axis. So this is my cylinder and I have this point P. So I'll have a tangent plane here. And first let me take this vector B to be parallel to Z axis. So B is just a vertical vector and B is also a unit vector also. So first let us take, so let B be parallel to Z axis. Okay. And let us take, let B equal to B1, B2, B3. Okay. So because B is parallel to Z axis, so this will imply that so this B1 and B2 are constant. Let us take this B1 to be equal to C1 and B2 to be equal to C2. Okay. So now let us take, so let alpha T equal to P plus TB. So alpha 0 is equal to P, and if I take alpha dot 0, so this will be equal to B. Okay. Okay. Now, if I take the differential in DNP, so DNP of alpha dot 0, so this will be equal to limit t tends to 0, n alpha t minus n alpha 0 whole divided by t. So this will be equal to what? So limit t tends to 0. So n of alpha t is equal to what? So it is n of p plus tb minus n of p whole divided by t. Okay. So now let us take this p to be equal to p1, p2, p3 and b to be equal to b1, b2, b3. Okay. So this b is parallel to z axis. So that will imply that this b1 and b2 are constant and they are in fact they are equal to 0. Okay. So therefore this limit t tends to 0. So this will be equal to the following thing. So the definition of n is as follows. So n of x comma y comma z is equal to x comma y comma 0. So therefore, so this will be equal to P1 plus TB1 comma P2 plus TB2 comma 0 minus P1 comma P2 comma 0. So whole divided by T. So this will be equal to limit T tends to 0, TB1 comma TB2 comma 0 whole divided by T. So this is equal to B1 comma B2 comma 0, but B1 and B2 are 0. So therefore, this is equal to 0. Okay. So therefore, so this DNP of alpha dot 0 is equal to the 0 vector. Okay. So now this is about this vector B. It is parallel to z-axis. Now let us take a vector which is parallel to xy plane. So next case, let us take this vector B be parallel to xy plane. Okay. So then B will be of this form. So B will be equal to B1 comma B2 comma 0. And let P equal to P1 comma P2 comma P3. Let me draw a picture. So this is my cylinder. Suppose this is my point P and I have this horizontal vector B. Okay, now I want to find a curve on the cylinder, so which passes through P and its velocity vector is given by the vector P at the point P. So let alpha T is equal to P1 cos T plus P1 sin T, comma P2 cos T plus P2 sin T, comma P3. So this alpha, it is this circle inside the cylinder. This alpha, it is this horizontal circle in the cylinder passing through the point P. And at t equals to 0, the velocity vector of this curve is equal to B. So alpha 0 is equal to P1 comma P2 comma P3, which is equal to P, and alpha dot T is equal to minus P1 sin T plus B1 cos T minus P2 sin T plus B2 cos T comma 0, and alpha dot 0 is equal to B1 comma B2 comma 0, which is equal to P. Now, in order to find the second fundamental form, so what you do, you take this Gauss map and take the differential. So T and P of alpha dot 0 we have to evaluate. So this will be equal to limit T tends to 0 n alpha T minus n alpha 0 whole divided by t. This will be equal to limit t tends to 0. So n of alpha t, so this will be equal to p1 cos t plus p1 sin t, comma p2 cos t plus p2 sin t, comma 0 minus, so what is n of alpha 0? It is p1 comma p2 comma 0 whole divided by t. So this is equal to limit t tends to 0 p1 cos t minus 1 whole divided by t, comma, plus p1 sin t by t, comma, p2 cos t minus 1 divided by t plus p2 sin t divided by t, comma, 0. So therefore, DNP of alpha dot 0, so limit t tends to 0, cos t minus 1 divided by t is equal to 0, and limit t tends to 0, sin t by t is equal to 1. So therefore, we have the following result. So this will be equal to p1, comma, p2, comma, 0. So which is again equal to p, which is equal to alpha dot 0. Okay. So therefore, so what we have now, so this second fundamental form, okay, so it depends upon this vectors, okay. So D and P is equal to 0. So if P is parallel to z axis, okay, so this will imply that pi p b is equal to 0. So if p is parallel to z axis, t and p is equal to b if b is parallel to xy plane. So this will imply that pi p b is equal to minus inner product of t and pb with b. So therefore, this will be equal to minus of norm b square. Okay. Yeah. So pi b is equal to minus norm of b square if b is parallel to xy plane. Okay. So now in terms of local coordinate, so how do I get this second fundamental form? So let sigma ub is equal to cos u, comma, sin u, comma, p. Okay, and what will be the normal on sigma ub? So n ub, so this will be equal to cos u, comma, sin u, comma, 0. Okay, so now you can compute the coefficients of the second fundamental form. So L, it is equal to the inner product of the partial derivative of n with u with partial derivative of sigma with u or sigma u. So this is, if we take this inner product, so this will be equal to 1. Okay, so note that here, so nu partial derivative means, so each component you are taking the partial derivative. So nu, so here it will be equal to minus sin u comma cos u comma 0 sigma u. So this will be equal to minus sin u cos u comma 0 sigma b. So this will be equal to 0 comma 0 comma 1 and nb. So this will be equal to 0 comma 0 comma 0. So you can evaluate this L, which is equal to the inner product of nu and sigma u, that will be equal to 1. M, it is the inner product of this nu with sigma b, which is equal to 0, and n is equal to the inner product of nb with sigma b, which is again equal to 0. So therefore, the second fundamental form is given as L du square plus twice m du dv plus n dv square. So this is equal to just du square. Okay, the second fundamental form in terms of local coordinate is equal to du square. Okay, I'll stop here. We'll continue in the next class.